Hello, and welcome to this session on using FPGAs in industrial use cases. I'm Adam Taylor, and we've talked a lot about FPGAs over the years, so hopefully you'll be familiar with me. And today we're going to take a little bit of a look through how we can use FPGAs in industrial applications. And there are several use cases for this as we come through it. The first one is the one that we think about most often, the precision robotics on the assembly line, either assembling the product or in some way or form interacting and working with that product. We also think about machine vision and AI at the edge. Again, that's potentially within a industrial application where it's doing some defect inspections, it's looking at the machines or looking at the products that's coming down the production line and making sure that everything is nice and happy there. While we think of that, there are other applications, that are outside the industrial, the factory floor. There's a lot of applications where we want to do some real-time signal processing. Examples of that would be where we want to do some really accurate control, maybe accurate motor control, or maybe accurate thermal and temperature control, as we're going to be talking about. There are other examples as well. So we can take a look at communication. FPGAs are brilliant for giving us bespoke communication between one point and the other point. So they allow us to bridge protocols, for example, from perhaps a Modbus protocol to an Ethernet protocol, or maybe to go from our operational technology network to our information technology network. They allow us to do that bridging due to their flexibility and use cases. So you find a lot of FPGAs in those industrial use cases. If we're doing test and measurement, for example, most oscilloscopes, most electronic test equipment, is heavily based around using FPGAs in there to be able to capture the data and post-process the data before it's displayed in a manner that we can then look at and work out why our systems are experiencing issues. There are other things we can do with it as well, such as instrumentation, and that's one of the things we're going to take a look at today, is where we want to particularly monitor or control a part of a circuit. So in this webinar, we're going to be taking a look at how we can use industrial automation and industrial instrumentation to create a precision analog solution. And we're going to build that based around a Spartan 7 board. So why might we want to use an FPGA in here? And FPGAs are actually pretty key to this. So we have a parallel architecture within our FPGA, and those CLBs, those configurable logic blocks within the clock regions, within the FPGA, all mean that when we come to create our solution, we're able to create a parallel architecture and where we can implement specific functional blocks. So we can have one function talking to the next function, talking to the next function, talking to the next. And it's implemented directly in programmable logic. So it's very deterministic and very fast. It also gives us a very low latency response. So not only is the processing time deterministic, but it gives us a low latency response. And that's what we want when we're working on, for example, a production line, or we've got precision motor control, or we're interacting with the environment. We need to be able to have that deterministic and low latency response. One of the nice things about FPGAs as well, obviously, is that we can do a chip down design and design it into a custom implementation. Or we could use a system on module or a tile-based approach as well, where we can drop that into a wider solution. And that's very important because it allows us to be able to pick the right solution for the challenge at hand. So we can do the chip down, or we can leverage an existing module or SOM. And because of that flexibility of the I/O around the FPGA, it means that we're pretty much the right PHY on the board, because maybe we need a little bit of translation between logic levels and the actual bus signal levels. We can support pretty much any communication protocol that we need to work with. It just becomes a case of implementing it and finding the right IP core or developing the right IP core to implement that. Obviously, as we move on into the world, we're at the edge in many industrial applications. And when we're at the edge, that means that we're susceptible to unauthorized access and potentially modification. And we need to ensure that there is no way that our designs can be modified or accessed or changed by an unauthorized user. So we need to think about the security that comes into the FPGA to give us that functionality at the edge. And increasingly with post-quantum cryptography, that's really important, because post-quantum cryptography means that many of the algorithms may be broken quite easily, particularly if they're based around primes and factoring of primes. So as we move towards the post-quantum cryptography world, that security is also important, and you'll see that rolling out in things like the Spartan 7 Ultrascale Plus family. And of course, we want a longer-term support for many industrial applications, because they're deployed in the field for not just a year or 2 years, but 10 years, 20 years, 30 years. And that's where FPGAs are great, because the AMD FPGA lines, they're guaranteed to 2035 and beyond in many instances, or even longer, which means that our challenges for obsolescence are reduced, because it's an easier solution to get through and to be able to design in. And if we've used a SOM approach or something like that, or a custom module approach, then of course that obsolescence is also in other components is also addressed and challenged by developers as they go through their normal manufacturing and obsolescence updates. So it can ease your challenges. So if we look a little bit more in detail in the FPGA, into the FPGA, we've got that fabric which helps us. We've got those resources, we've got the fabric, we've got that parallel and flexible architecture. We also find that in many FPGAs these days, they're not really FPGAs, but they're heterogeneous system on chips, and that brings with it advanced processing cores such as the ARM A9s in the Zinc, the A53s in the Ultrascale Plus, and the A72s in the Versal devices. And of course, the Zinc Ultrascale Plus and the Versal devices also have real-time processors based in there as well, not just the application processors. So that means we can do that system segmentation between the sequential world and the parallel world, and bring it together nicely to make it all work, and it gives us the most efficient solution going. Now, when you think about a lot of industrial control applications, would be it sort of advanced motor control and synchronization, critical functionality such as we're doing, which is precision measurement and temperature, you need a lot of mathematics to be done, and you need that mathematics to be done very quickly, because we've got short decision loops and low latency to ensure that we can safely operate in the environment that we are. So those DSP elements that are embedded within the FPGA really come into their own, because if we're doing filtering or multiplication or PWM or AI or ML, they really become very powerful to help us to be able to do that. Of course, these days, FPGAs are very complex, and they all contain either what's called the XADC in the 7 series, or the system monitor in the Ultrascale and the Ultrascale Plus series. And this is a 12-bit analog to digital converter that allows us to be able to see up to 16 analog differential inputs. So we can do precision measurements using ADCs that are built into the FPGA. And nicer than that, we can also measure the FPGA's own power supplies and temperature to ensure that we're looking at the safety of the device, and that we're looking at the security of the device as well. So if anybody tries to do anything, that can help us. We have a range of I/O, and we touched on it briefly a minute ago when we talked about the any-to-any connectivity and communication standards. But it really is important to dive a little bit deeper in and take a look at it. So we have the high range FPGA I/O, which is going to give us 0 to 3.3 volts, and that's going to allow us to interface to some legacy sensors and some slower speed sensors. Things that connect over SPI, I2C, for example. Accelerometers, pressure sensors, things like that. We can use the high range for. We've got high performance I/O, which give us really high performance, really differential support as well. So if we're working with image sensors, for example, if we're doing a production line inspection industrial application, those high performance I/Os can connect to that image sensor, and they can stream in the image data at the rates that are coming in at 4K by at 60 frames per second using MIPI or something like that. So they're really there to give us that nice flexibility of interfacing. And then the XFIs, They give us, if we want advanced memory solutions such as DDR4, DDR5, that means that we can actually easily connect with that and actually then work with that memory very effectively, and use it, if, for example, in our image processing application, as a frame buffer or something along those lines. Well, that's the device looked at, and we've also got to look at the flow that we get within the tool itself. So we have the isolation flow that allows us to look at the clock regions in the FPGA, the resources in the FPGA, and to isolate functionality away from each other. So this is very important if we're doing safety critical solutions, for example, IEC 61508 or ISO 26262. And we want to have, we've implemented, for example, functions, and we're doing some voting, but we want to make sure the functions can't interfere with each other. We can use that isolation flow to segment and away critical functions in our FPGA design, in our FPGA floor plan. Of course, being an SRAM based FPGA, there is the chance that you may see some single event effects. And that's particularly true that at altitude, not so much at ground level. But just to be on the safe side, there is the single event mitigation IP, which scrubs the configuration memory and ensures that the FPGA is correctly configured and working. And the single event mitigation IP, in collaboration with the isolation flow, really gives us a nice, safe, and secure implementation of our design. To give us a secure configuration as well, we can use the security configuration and the runtime security and secure boot features of the FPGA to make sure that when our device is deployed at the edge, it is as safe and secure as it can possibly be, not just today, but also in the future. Now, one of the challenges that we get when we think about doing industrial control is why not use a PLC? And as engineers, we're typically, paid to pick the right application for the task in hand. So for some applications, a PLC is sensible. They're typically software processors that run a dedicated operating system. They use a very specific programming language, such as ladder logic or functional diagrams to control. But actually, they hit some issues because fast calculations or fast die updates can be a challenge because they work in this sequential nature where they basically sample the inputs, they calculate what the new outputs are, and then they update the outputs, and then they move around in that sequence for forever in a day. So it's a sequential solution, and that's not so good perhaps when we need that fast, immediate, quick solution when we're working on that industrial production line, or we're working with robotics where people are interacting with them. So because FPGAs are truly parallel in nature and have that flexible I/O, so we can interface with a range of I/O, FPGAs generally tend to be a better solution for many applications. But it's like everything in life. There are pros and cons for everything. But wherever you want to do that high speed, that correct sort of that sub-microsecond response, and you want a very deterministic, very low latency response, then the FPGA wins. And it also wins if you want a customizable solution, so if you want to be able to interface into a range of different solutions, of different sensors, different actuators. If you've got complex algorithms or high-speed processing that you want to win out, then FPGAs are generally a much better choice to run through than PLCs. They are obviously, they require a little bit more thought and a little bit more design, but the return on investment can be quite a significant solution for many applications. So in this project today, we're going to take a look at how we can create a thermal control application. And this is important because many applications require accurate thermal control. And we've designed electronics and FPGAs to do this before, particularly for camera systems. We've done this for a lot of camera systems for perhaps for astronomical cameras, and things like that, where you want to make sure that the cameras are set at a very stable temperature. Because if they're not at a stable temperature, then what happens is noise within the image can creep in, and you can cause some issues. So the more stable you can make your camera system thermally, the better and the more higher performance you get. So we do this, we're going to do this today using a ratiometric approach. And to do this, we're going to use some simple analog components. We're going to use a digital to analog converter, the analog to digital converter, the XADC, the system monitor that's built into the FPGA. And this is a similar approach that I've seen used in a lot of applications, and it's a very useful approach, because if you do a ratiometric approach, we're basically measuring the difference between two measurements that we take in our system. So any drifts, any aging, any changes in voltage references, or AD or bias currents, or trace resistance, or thermocouple junctions as things change, it's going to be calibrated out due to that ratiometric approach. It might sound like it's actually quite a complex solution, but actually using the XADC and a simple DAC and a few as for the reference, and then a few precision resistors and a temperature sensor such as a thermistor, we can actually get quite a nice and effective solution out there. So like I say, well, let's touch a little bit more on what ratiometric design is. And it's a technique used to improve the accuracy and stability of analog sensor readings. And it does this by allowing us to remove the impacts of fluctuations in supply voltage or current, or any other systematic issues, because we're measuring two proportional signals, and we're using the ratio between those two measurements to determine the actual value. And as I said, you know, by using the ratio of these two measurements, the measurement's going to become independent of the actual value of the excitation, and therefore, because of that, any variation is going to cancel out as we go through it. This method's really powerful for really sort of precision analog measurements and precision things. So if we're doing things such as wanting to measure temperatures or strain measurements or bridge circuits, this is a really good solution that we can bring in and leverage and use. So our analog front end is going to look very simple, very similar to this diagram here. We're going to have two drive elements. We're going to have drive element A and drive element B, and this is where we're going to apply the excitation. We're going to have a thermistor, which is shown as RT on this diagram, and then we're going to have a 1K resistor also. And then we're going to have two current limiting resistors at 2.2K. Now the 1K, the 2K, and the 2.2K resistors, they would be precision resistors. To get the best out of this, they would be precision resistors. To understand a little bit about how the system works and how it works, you know, standard sort of off-the-shelf resistors will be okay to give you a bit of a view, but for deployment, you'll need to use precision resistors. Then what we have is we're taking the measurement across the thermistor and across the 1K into the XADC. Now in this, we're going to take this into the auxiliary channels of the XADC. So the XADC has a dedicated VP-VM pair, and then it has 16 other auxiliary inputs. The only difference is the auxiliary ones are not dedicated, they're shared with digital I/O, so they have a slightly lower bandwidth that they can sample signals at. But we're measuring pretty much DC signals here, so we're okay to do that. And the reason that we're measuring the auxiliary channels is that I want to make sure that everything is identical as possible across the thermistor and across the 1K resistor. So it's a very simple measurement that we're going to be taking. Now, what we can do is we can use drive A and drive B, and we can drive that from a digital to analog converter. And to get the best performance from this, what we can do is we can use drive A and B, and we can drive them one way where we set A positive and B negative, and then we can take another measurement where we actually drive A negative and B positive, and then we can take those measurements as we go through, and that will also help us with measuring out and removing any differences within the system. So that drive in reverse, you know, the flowing the current in the opposite direction, it means that we can, you know, it means it helps us get a more accurate result. So you can see our final result is shown down there, down at the bottom, where we're going to calculate these simple simple resistor. Now we're actually going to do this. We're not going to implement that in the FPGA. We're going to use we're going to use a small, we're going to use the processor cores to do that. But we can implement that very simply and easily. But the FPGA gives us this flexibility to do this. So in our project, it's going to be quite simple how we're going to do this. We're going to use the PMOD DA4 to provide the reference current, and we're going to use 2 channels of the XADC that's going to be used to perform the measurements. And to be honest, because we're doing that differential, we're doing the differential measurements, we need to make sure that we've configured for differential measurements in our XADC as we come to it, and we'll take a look at it. Not one that's configured for doing a unipolar measurement either. So we can work that out as we go through it. So let's take a look. So at the analog front end, so the design is we've designed it to use this differential ratiometric analog approach. We've got a 10K negative temperature coefficient thermistor and a 1K precision reference resistor. What we're going to do is we're going to put a 0.5 volt excitation across the resistor network, and that's going to give us a current of approximately 32.5 microamps that's going to flow. The current is set through the 2.2K resistors on either side, and we're going to use the auxiliary channel 0 to measure the voltage across the thermistor, and the auxiliary channel 8 to measure the voltage across the reference resistor. Because both the thermistor and the reference resistor are driven by the same current, the system, we can then use the ratiometric approach to calculate the value of the resistance of the thermistor using that equation that's shown there on the bottom. So if we take a look, just to summarize what we've got on our analog front end, and for this process, you can see it's a fairly straightforward and a fairly simple solution that we have on a little breadboard, and we just used a breadboard to prototype this and prove out this solution. So we can have a 0.5 volt excitation voltage. This responds nicely to the voltages that the XADC can support. We have this 32.5 microamp constant current. We've got the 10K negative temperature coefficient thermistor with a beta value there. We've got the reference resistor. We've got the safe temperature range. We're going to be able to monitor from, say, 0 to 100 C with this. And then we've talked a little bit about the measurement and how we're going to do it. So we're going to do this differential, this ratiometric via the XADC. And the ADC input range is going to be as is shown there. So this is going to give us, as we've said several times, it's going to give us a much better improved noise rejection ratio. It's going to help us minimize the impact of the power supply noise and other common mode signals. Because we've got everything there, we've got a balanced signal path, so the current is symmetrical for both the thermistor and the resistor. We've got a design that supports this bipolar excitation because we're using the digital to analog converter. So we can support bipolar excitation. We can drive A and B, positive and negative, and change it around that way. And that means that we've got this nice differential voltage measurement that comes across there. And it gives us this nice safe range that we can sit in for that. The accuracy is going to be pretty good, as you'll see as we get to the end, because again, we've got the same currents flowing. And in theory and in practice, we'll get a better thermal and layout stability because all of the drifts, all of the changes, it's all symmetric to both the resistor and the temperature sensing device. So it means that we're more stable over temperature and time, which is really important and really what we want to try and do. So let's take a little bit of a look now into our design. We're going to take a look at the XADC first. That sits within the FPGA. For this application, I use the Digilent Z board because that was the one that had got actually the most broken out auxiliary XADC channels on its XADC header. So we're going to use the XADC there. We're going to use the auxiliary channel 0 and 8. Because overall there's a 1 megasample sampling of the XADC, and that's true. But the auxiliary pins are that, you know, you can't put a signal more than 100 kilosamples per second into them due to that, how they are. But for us, we're measuring pretty much DC. You know, we're going to set the ADC, the DAC to one value. We're going to let it settle. We're going to take the measurements. We're going to flip that over, let it settle, take the measurements, calculate the output, and then move on. So it makes it nice and simple. Now, a little bit of an iteration to this circuit would be to use the same ADC. It would be to use a switch that means that the same ADC is used for both measurements as well. So we are getting as close a input path as possible. Our completed design is actually quite simple. You know, we're going to use the PMOD bridge to give us that access to the PMOD DA4. We're going to use the XADC wizard, and then we're going to use the processing system there sat up there to do the control. And we're going to write, majority of this we're going to write in software to run. If we wanted to do any filtering or further processing, we could do this in the FPGA, but to just prove this proof of concept, we're going to run this in the PS of the sync. Our software designer will take a look into our software design in detail in a little while, and that's going to show us how we can do it. So it's going to run through several steps. It's going to initialize the PS SPI, which is what's going to talk to the PMOD DA4 DAC. We're going to initialize the DAC and set up its internal references and power up the DAC. We're going to calculate the code that's going to give us the excitation voltage for the network, and then we're going to drive the DAC channels A and H, and we're going to alternate those to be outputting between 0.5 volts and 0 volts, as we were talking about. And that's going to mean that we can run the algorithm then, and then we can calculate this. So we'll take a look at the software in more detail in a minute. The completed system is going to look exactly like this, where we've got the DA4 connected into the Z board. We've got our little prototyping board there with our resistors on it. And like I said, this is all linked in a Hackster project as well. So I'll link in the Hackster project at the bottom of it as well. So you can take a look at the Hackster project and run through that Hackster project also. When it comes through to running our devices, obviously we want to get a nice, stable, nice solution. We can see that we get the ADC samples coming in. If we were to look at this and we were throwing this out to the terminal, so as we could see it, we get the reference voltage and the thermistor voltage. The voltages across there. They're very close. You know, it's not the best solution in the world of how we've implemented it, but it kind of works there. We can calculate the reference voltages as well as we're going across there further, and then we can see that we can calculate the temperature and get the temperature calculated coming on the actual output. So that's a nice solution that we've got there, and it's working quite closely and running through. So let's take a look at the detailed design. Let's take 5 minutes to take a look at the detailed design. We'll take a little bit of a look at the Vivado design, and then at the Vitus design. So let's just pop that onto the full screen. And as you can see, we're targeting the Z board. You can see that there from the summary of the events, although my machine always goes slow when it's running through this. We're not using a huge amount of the FPGA, but if we come back to our block design, the main important thing that I want to show or want to share is how the XADC is configured, because that's really quite important for us all. So let's just reconfigure that, recustomize that, and then we'll take a look at this as it goes through. But that XADC, like I say, it's really important to be able to give us that sampling of the external values. Once this opens in a second, we'll see that we've configured the XADC. You know, we've configured it to use an AXI4 Lite interface, as we can access it from the processing system nice and easily. We've set up the channel selection to do a channel sequencer. Now, if we wanted to process this and calculate this within the programmable logic itself, we would enable this AXI stream, and we would then create an IP block that did it. However, in this instance, we're not doing that. We've set the DRP timing. You know, we're going to give it a 100 megahertz clock, such that we get a 25 megahertz ADC clock. And if we take a look at the ADC setup, we've set this up to ensure that the gain, the offset and gain calibration is performed, the sensor offset and gain calibration is performed, and that we've enabled the calibration averaging as well. So we're trying to make sure that the sensor, the ADC, is configured to give us the best, the most accurate results going possible. We also we've enabled the channel averaging. So we're averaging this time, we're doing 64 sample averaging of the data as it's coming in. We've turned off pretty much all of the alarms because we're just doing this for a prototype at the moment, so we don't need to worry too much about the alarms. And then on our channel sequencer, we've enabled the channel sequencing on channel 0 and on channel 8. So the two auxiliary channels that I was talking about, we've just enabled, and we've enabled the average, and we've set them up for a bipolar input. So this is the summary then of our ADC solution on the XADC. We've connected this in obviously over the processing system using an AXI interconnect. And then what we've done, because there's no IP core to drive the PMOD DA4, but it's just a SPI type interface. So we've used the IP PMOD bridge IP from the Digilant IP core library. And what we've done is we've also configured the Zinc processing system to make the SPI external and available over that over the what's called the extended EMIO. So it's not going out over the PS MIO. It gives the SPI access to the programmable logic IO, and we've routed it then to the necessary PMOD port on the FPGA. So if we take a look at the MIO configuration here, and if we take a look at the IO peripherals, we can see that we've set the SPI 0 to be set to EMIO. So that makes it available to us in the programmable logic system. And like I say, we've connected that PMOD bridge onto the back end of it, and that gives us a nice and simple solution that we can work with. All we've got to do then is define our constraints, and we define our constraints as you can see here. So we've just defined the SPI signals here. So the chip select, the clock, the master in slave out, and the master out slave in on the relevant signals, and then we can build the application. We can then come over and pull this over into our software world. And when we bring it over into our software world, what we want is to create a application. And if we go up to the top, we create a platform with our exported XSA that's come from Vivado, and then we pull this into our Vitis application with that platform, and we create an embedded Vitis application on top of it. And there's a few things that we've done here. So we're using the Xilinx, the PS SPI. We're using the system monitor drivers. We're using the math.h, which means we need to make sure we map that in with our linker. We've set the base address for the SPI MIO. We've set a maximum count, and we've defined the SPI instance here as well for the DAC. So how this works is we have to set up the instance of the SPI, and then we can once the software APIs and the drivers know the base address of the SPI driver that they're using of SPI 0 that they're using in the Zinc, and the rest of its status, they can interact and send with it. We'll see here we've set up a simple output buffer with the correct formatting, with the correct words in it, to be able to correctly configure the PMOD DA4. And then we've set some other things up. So we've set up our reference resistor, and we've set up our system monitor instance as well. So we have an initialization function here. So within our initialization function, we've initialized the SPI, the PSSPI, with the base address. If it fails, then obviously we're not going to go any further with the program, but if it doesn't fail, we're going to pick it up and run for it. We're then going to set our options here. So we're going to set this SPI We're going to tell it the instance that we're working on. We've only got one SPI in there, but that's what we're working on. We're going to say that we want to have the master option and the clock phase that we want to use. We've then set the clock prescaler such that we're running at a reasonable clock rate and we're not running too fast for this XADC. Sorry, for the PMOD DA4. And then we're setting up some internal buffers to read and write the PMOD DA4. Once we've set those values that we want, that bring it, essentially they set the internal reference to be used in this first one. We do a polled transfer, so it will transfer those 4 bytes into the SPI, and then it will come back and we will power up the PMOD DA4. So the DAC that's on the PMOD DA4 will do that power up, and this gives us the power up that we can see here, and we can do that transaction there. Again, we do that transaction and it runs nicely. Once we're running, then we define a couple of processes. So if we've defined a couple of processes here, we've got to write to the registers. We've got to write to DAC A over SPI and to DAC H over SPI, and each one requires a number of bytes to be sent. So we have a positive direction to set the value for DAC A and DAC H in the positive direction, and we have a similar function as well underneath for doing DAC A and H when we want to do the flip and when we want to do the negative. Again, we're using the SPI poll transfers because it's really simple. We're just sending 4 bytes across into the PMOD DA4 just to set the voltages. We've also got a couple of other functions defined. So we've got a converting the value into the XADC value into a bipolar voltage. We've got the reading the XADC auxiliary channel and getting the ADC data from that. We've got a calculating the thermistor resistance temperature function that we use to do that thermistor calculation. And then we've got a thermistor resistance to temperature function as well. So we're going to take that resistance and we're going to convert it into a Celsius type application. Within our main application, it's going to come down and it's going to be nice and simple. We're going to run through the initialization of the XADC. Once we've done that, we're going to set the sequencer up again just as we want, although I know it's already configured in the IP core. We're just going to configure it again in software to make sure that it's doing exactly what we want. And we're going to put the sequencer into safe mode. We're going to enable the channel enables, and then we're going to start running that continuous pass on it. Once we've done that, we're just going to have a simple loop, and it's going to be a really simple loop. It's going to set the channels into the positive direction. We're going to sleep for a second to make sure that it's in the right format. Then we're going to do the reading of the auxiliary channel. So we're going to read the auxiliary channel 8, read the auxiliary channel 0, and put those into the thermistor and the reference voltages. If you want, we can then print those out for debugging so as we can see where we're going. Then we're going to wait a little longer. We're going to set the negative direction. We're going to wait for the voltages to stabilize again, and then again we're going to read those voltages and store them in these variables, and then we're going to calculate what those voltages actually are for the reference and for the thermistor. Again, a little bit more debugging code if you want, but that's not included and not necessary in this. And then in this application here, we have the floating solution, calculate the floating value of the resistor, so the thermal resistance, and then basically calculate the actual temperature that we're seeing in the system, and then we can correlate that against the temperature that we see in the environment and make sure that it's calibrated and working okay. When we did this, we were quite easily seeing that the temperature was running through and was showing a nice and accurate temperature. Obviously, if you design this on a proper printed circuit board with proper resistors of the correct precision and such like, you'll get a much better result than what we did. But to demonstrate the principle and the theory of it, you know, this is a really nice and really simple project, and it shows you just how easy it can be. And like I said, this is a Hackster project. So if you want, you can take a look at this Hackster project here. Let's pull this onto the screen. Just a second, we'll pull this on. And this Hackster precision analog, it's going to take you through. You can do this with a range of boards. There's nothing too complicated about it. But pretty much everything we've talked about in this session today is going to be shown through in here. And there's a little bit more detail in it as well, as it's going to walk you through the settings of everything and how to recreate it and how to make it all work and come together. And that's going to bring us to pretty much the end of this solution. You know, we've demonstrated how we can use industrial use cases for FPGAs, why we might want to use FPGAs for industrial use cases. We've outlined the differences when we might want to use them between PLCs and FPGAs. And we've demonstrated that we can create a really nice solution really quickly and simply and easily using that approach as we've outlined. And take a look at the Hackster project as well if you want to know more or you want to try to recreate it. And with that, I'll thank you for your time and attendance. I'll apologize for the slightly weird behavior of the Livestone platform that we had earlier on that made it terminate early. But hopefully you can all see this recording and it makes sense. And if you've got any questions, please reach out to me across social media on LinkedIn or Twitter or email, and we'll get back to you and answer those questions. But thank you very much.